All right, in this video, we are going to be talking about multiple regression. And multiple regression is for me where things start to get really fun and interesting. We'll talk a little bit about how multiple regression can do a lot of the analyses we've talked about through the course, but multiple regression starts to be flexible enough that I can use it in a bunch of different circumstances, and this starts to get into the tools that I most commonly use in my work. Now, actually, I shouldn't say that. I use ANOVA, I use chi-squared, I use t-tests, but regression is unique in that regression starts to let me, specifically multiple regression, starts to let me do the cool statistics that people are looking for. What it lets me start to do is make conclusions about the relationships between two variables while controlling for a third variable. So I want to look at the relationship between weight and height while controlling for age or something like this. I want to look at the relationship between the number of ads on the TV and number of cars I sell while controlling for, let's say, the weather outside or something else that maybe is an important factor. Maybe I want to study that second variable too. Maybe that second variable is not important at all, and I just want to take that out of my considerations. That is, I don't want that to be a possible explanation of the outcome. I just want to account for that. Multiple regression lets me do those things. And that's why this starts to be really cool, at least for me. It gets sad because there's so many things we can do with multiple regression. This really is opening Pandora's box in terms of your analytical skills, because you can just start dropping pieces in that you want to use and want to take advantage of. So at its base, multiple regression is just this simple linear regression that we talked about, except for multiple regression allows us to have more independent variables. And again, the nuance of this and the fact that this is opening Pandora's box may not be completely clear yet, but we'll get there by the end of this lecture set. So ultimately, with more independent variables, I'll call the new independent variables different x's with a different subscript under it. So this will be the first independent variable, x1, the second independent variable, x2. Each one of these are going to have their own little betas. And maybe in the simple linear regression, you wondered why we started with 0. Well, this is actually the reason we started with beta 0 instead of starting with beta 1, is so that the first independent variable can have a beta with a little sub 1 next to it as well. The second independent variable can have a beta with a little sub 2 next to it as well. Because if we started at beta 1 and then beta 2 times x1 and beta 3 times x2, that'd get really, really confusing. So the beta 1 goes with the first independent variable, beta 2 with the second independent variable, and so on. Now, just like before, we talked about the error is going to be there. It wasn't there in the last slide for the individual y value, but for the expected y value, the line, well, we're not going to be talking about a line anymore. We've got as many dimensions as we have variables. So with just one independent variable, we had 2 dimensions. With 2 independent variables, we're going to have 3 dimensions and be predicting a plane. So think about a sheet of paper going in 3 dimensions. That would be with 2 independent variables. And then with 3 independent variables, we're past good visualizations. Now we're onto hyperplanes and stuff like that. So we're not even going to talk about visualizing some of this. But going back to our simple linear regression stuff, where we could visualize this easily, the expected value relationship was talking about a line that is our predicted value. And the line doesn't need a space to cover the dots because it's just going to be a line. The actual observed values on the previous slide, that needs the error so that we can have the dots that are different than the line. Our estimated equation, just like before, we're going to use lowercase b's instead of the betas to represent the estimated values. And the structure looks like before. Don't get concerned, intimidated by all of the different values here. Just think about we've got multiple independent variables. And so we start with the model. That is, we start by identifying what do I want to be the outcome? What do I want to see if it affects it? So let's say I want the outcome to be the cars I sold, and I want to see if the number of TV ads affects that, and I want to see if the number or the weather affects that. So I'll say sunny day or rainy day. And I want to see if those 2 variables affect the number of cars sold. Then I go from that, this model or this idea of what I want to study, to collecting data on that. And then I make guesses as to how much does the TV ads affect the outcome, the number of cars sold, and how much does the weather affect the number of cars sold? And the cool part again about multiple regression is I get to make claims about TV ads after accounting for weather, and then weather after accounting for TV ads. I then go to estimates, parameter estimates, these guesses, and then I can use that to inform my original theory. Now, we talked about we have to figure out how to find the best line. And in this case, we have to figure out how to find the best line or plane if we have two independent variables, or hyperplane if we have three or more independent variables. And it turns out that as long as you're dealing with this linear, like with these, just the b's and not do anything fancy with the b's, you just have as many variables as you want with a little b in front of it. And you're not have a little square root of b or b squared or e to the b value squared, like any crazy things with your b's. As long as they're just regular b's, you can still use this squared method and it still works pretty well. Now, I think it mentions here, we're not really going to talk about how to do the calculation. It's not that it's too bad. Actually, I can write out the equation for you for doing the calculation. Well, I'll write out the full model. Y equals x beta plus epsilon. Then we have x transpose x quantity inverse x transpose y. And these will have squiggles under them. All right, so this is my estimates for my betas, beta hat vector. So you have to get in a matrix form, and that's the trick. But this is a pretty short equation. Like solving this by hand is a big pain in the butt, but the equation itself, x transpose x inverse x transpose y, like I can at least write that pretty small. So the idea behind how you solve these is not particularly difficult. I will say the idea behind the solution is exactly like the solution we talked about for beta 1. The weird thing here is that we're expressing it in matrix form. So we had x times y, the sum of that in the numerator, and then we had x squared summed in the denominator, and the minus 1 says put that in the denominator, kind of. It's a little different in matrix form, but if these were scalars, that would be the case. So it pretty much is the same thing, x times y in the numerator and x squared in the denominator, and that gives us our betas, pretty much the same thing as we had before. And we're not going to talk about the matrix stuff. I just thought you might find it interesting. We're going to be using the computer and just focusing on interpreting. All right, so in this particular case, we're looking at 20 computer programmers. Suggestions made that we could use regression to see if salaries related to years of experience and the score on the programmer test. So is this where the salary is coming from? Salary maybe is coming from two things. It's maybe coming from years of experience, and maybe it's coming from how talented you are according to the aptitude test. And let's see if there's a relationship here. Now note that if we use multiple regression, we'd be accounting for the effect of years of experience after accounting for aptitude. And we'd be accounting for aptitude after accounting for years of experience. I'll say I just had a presentation get presented at a national conference where we discussed how sometimes this is not necessarily a good thing. Sometimes you don't want to do these after accounting for one another, but often it is a good thing. Often it's really nice to see, well, what is the unique effect of years of experience on salary, and what is the unique effect of programmer's aptitude on salary? Again, after accounting for years of experience. Because obviously, if you're here for 30 years, you're going to have a higher aptitude. That's not what I'm trying to study. I'm trying to see, is your aptitude affecting salary outside of your years of experience? So in this case, this is a really good thing that they're taking into account. And most of the time it is, but there's a couple of unique situations where maybe it's a little bit more problematic than it is helpful. All right, so we collect data on this. And again, this is how the process goes. We think about the question we want to ask, and then we go collect data. Here's our data. I've got 20 individuals. 10 are listed here, 10 are listed there. Each row is a different individual. So this is person 1, this is person number 11. These are not the same. And so I've got their experience, their test score, and their salary in thousands of dollars. Now I've got my model, so maybe if I were writing this out, sometimes it's nice to have salary equals the x1 is experience. I'll write exp. Oh my gosh, my handwriting's terrible. exp, and then I may write apt. So sometimes instead of x1 and x2 and y, it's nice to write out the words so that you can see what you're talking about here. You don't have to do this, but sometimes it is nice. And they do write out a definition list down below. And so I'm going to take my data, I'm going to plug it into a computer, and then I'm going to get my output. Our textbook doesn't even try here, and that's just fine. Again, typically, once we get to multiple regression, in fact, when I used to teach this from my math program, I'd have a whole chapter on matrices right before this. And so we talk about all the matrices, we talk about all the matrix calculations. That really is how you do the calculations for this. You don't try to do it using scalar or regular numbers. And then I get my regression output. Now this is going to look exactly the same as our regression output from simple linear regression. I've got a constant, but now I'm going to have two lines for two different independent variables. And I can interpret these as the, well, we'll talk about interpretation in a second. But notice I've got two lines, I've got two standard errors, I've got two t-tests, and I've got two sets of p-values. Now remember, I don't do interpretation for the parameter estimate until I have looked at the p-value. Both of these are statistically significant at the 0.05 level, so I can do interpretation. Now I can plug in the values into my equation. So this is the estimate for B0, and maybe I'll write these next to each other. Remember the coefficient B0, the constant, the intercept of B0. The experience was B1. And B2 is going to be my test score. So that's what these are estimates of. And I can just go on and plug those in the equation. That makes it nice and readable all in one place. And now we can go to interpretation. So the B1 values, 1.404, is the expected increase in salary for each additional year of experience. Now note that all of these B1s represent the change in Y when we have a 1 unit increase in X. So this is just like before. But what's unique is this end statement here, when all other independent variables are held constant. So going back to the interpretation, we expect salary to go up 1.404 thousands, or $1,404 for each additional year of experience when the variable on score programmer aptitude test is held constant. So here you are holding this, I thought it was aptitude. Yeah, this is a typo. It should be aptitude. Sorry. So when aptitude is held constant, this is what your expected increase is, or your average increase in salary is. So for each additional year, you're going to make, on average, about $1,500 more bucks. Kind of averaged across your programmer aptitude, so not taking into account your programmer aptitude. Now down here, B2, now we're talking about the effect of programmer aptitude on salary. So salary is expected to go up by $251 for each additional point scored on the programmer aptitude test. Now you can multiply this by a constant. So if you said I wanted to go up not by a single point, but I wanted to go up by 10 points on the programmer aptitude test, then this would be multiplied by 10. So this would be going up by $2,510 for every 10 points you go up on the programmer aptitude test. So sometimes that can be nice when a single point increase doesn't mean much, but maybe a 10 or 100 point increase means a lot more. In this case, I think a single point increase on the aptitude test probably isn't that meaningful, but maybe a 10 point increase on the aptitude test is pretty meaningful. So a $2,500 bump for a 10-point increase on the aptitude test, or a $251 bump for every point increase on the aptitude test. But note that this is when years of experience is held constant. So this is not accounting for years of experience, or excuse me, this is accounting for years of experience. This is not needing that years of experience to change. This is holding that years of experience to be constant. Really what this does behind the scenes is averages this growth over all of the years of experience. All right, so just like we had the ANOVA breakdown of the regression in simple linear regression, we can do this with multiple linear regression as well. Now, this is going to be a little bit more meaningful. So we just talked about each of the different parameter estimates, and we saw that the table had different statistical tests for each one of those. But in this one, now we can talk about, because we have this breakdown, that overall F-test where we use the sum of squares regression and sum of squares error and sum of squares treatment and come up with that overall F-test that's going to be nice. We'll talk about that in a second, but we can also talk about this multiple coefficient of determination where we can look at the percentage of variance explained by all of the variables in the model. So in this particular case, I'm going to pull my sums of squares, my sum of squares regression, my sum of squares total, and then find the ratio between them. In this particular case, how much of the variability in the total, the 599 sum of squares, is explained by the model, the regression model, 500 sum of squares. 500 divided by 599 gives me 0.83. So about 83% of the variability, the total variability, is explained by my model, which accounts for programmer aptitude and years of service. So that says programmer aptitude and years of service is explaining a lot of the variability in the total salary in my data. Now, one interesting thing comes up when we're dealing with multiple independent variables, and that is literally every single time you add an independent variable, literally every one, no matter how bad the independent variable is. I added the length of your left hair's longest, your left nose's longest nose hair, like the most bizarre, random, whatever, unrelated, bizarre, weird thing. And that was pretty bizarre. I'm pretty sure that was you didn't expect me to say that. Okay, so I'm using that measurement and tossing it into my model. When I add that, even though that is completely unrelated to anything, that will always cause your R squared, or the quote unquote percentage of variation explained, to increase every single time. And that was the most random, bizarre thing I could think of. Yeah, okay. I don't even know why I could think of that. That's kind of weird. But that's the most random thing I could think of. Okay, that will cause your R squared to increase if I added that into this model explaining a programmer's salary. Well, that seems kind of weird. That doesn't seem like it should meaningfully explain any variation in your salary. That seems like it should be completely unrelated to anything. And if you think that, you'd be exactly right. So this is kind of like a weird thing that's wrong about our statistics. That should not happen. So to account for this, we don't always use the regular coefficient of determination. Sometimes we use something called an adjusted coefficient of determination to help to compensate for that fact. The equation starts out with your regular coefficient of determination and multiplies by this, where n is the sample size and p is the number of independent variables you have. So in this case, I've got 20. So my sample size, I've got 2 independent variables. And so I'd multiply by this. And in this case, this is supposed to give me a bit of a better estimate. What's interesting about this is if you add something like the variable I mentioned earlier, again, this pretty bizarre out of nowhere variable that really doesn't relate to anything. Instead of continuing to go up every time, your R squared, this adjusted one, will actually decrease slightly to indicate that really you're explaining less variability with this new independent variable that you have. All right, well, this has been our opening day on multiple regression. Again, opening this cool Pandora's box of stuff. In the next video, we'll be talking about some assumptions that we can test. It's going to look very similar to simple linear regression, but we'll be talking about some of the assumptions we can test in our model.